Chatbots powered by LLMs and RAG offer advanced conversational capabilities. They combine the depth of pre-trained language understanding with the ability to pull in relevant information from external sources. Starting from the left side of this diagram, this proof of concept begins with the web-based user interface where you can ask the Llama 3.1 model questions. A Redis vector database, preloaded with vectorized data from a PDF document, supports this process. The web GUI sends the same question to both a non-RAG backend and a RAG backend. Both backends interact with the Llama 3.1 model server running on OpenShift AI using S3 storage to load the model. The RAG backend queries the vector database to provide additional context to the answers. Red Hat OpenShift AI provides an integrated MLOps platform for managing the lifecycle of predictive and generative AI models at scale across hybrid cloud environments. In my OpenShift cluster, several operators enable this proof of concept. Node feature discovery labels nodes with their capabilities, including Intel Gaudi. The Intel Gaudi AI accelerator operator installs the necessary driver, Habana runtime, and a metrics exporter. Kernel module management assists with driver installation. The Red Hat OpenShift AI operator, along with OpenShift serverless and service mesh operators, installs and scales AI models on OpenShift AI. If you look at the node details, you can see that 8 Intel Gaudi AI accelerators are exposed and available to schedule. From within OpenShift AI under serving runtimes, there is a TGI Gaudi runtime that is configured for serving a Llama 3.1 model. Serving runtimes are used to deploy and manage machine learning models. An accelerator profile for Intel Gaudi is added, allowing you to choose from 1 to 8 Gaudi units when serving a model. These profiles optimize and manage AI workload deployment on hardware accelerators. In my data science projects, I'm serving a Llama 3.1 model using 4 Intel Gaudi AI accelerators with the TGI Gaudi runtime. The model is already deployed and ready for use. Going back to OpenShift and looking at the running pods in my Gaudi demo namespace, you can see there are 4 pods running. There is the UI demo pod, which is the web interface that sends the question to both the RAG and the non-RAG backends. There are 2 backend pods, one for non-RAG queries, which directly interfaces with the Llama 3.1 model, and one for RAG queries, which uses the Redis database to add contextual information. Finally, the Redis vector database pod supports the RAG backend. It processes PDFs by extracting, chunking, and embedding text, storing these embeddings in the database to provide additional context to the Llama 3.1 model. In my Gaudi Llama namespace, the AI model is deployed and running with 4 Intel Gaudi AI accelerators. From the web interface, let's ask a question without additional RAG context. Both the non-RAG and RAG backends provide good answers, and the responses are roughly the same. Now, let's ask about the memory of an Intel Gaudi 3, which the Llama 3.1 model wouldn't know. On the left, the non-RAG backend gives a wrong, hallucinated answer. On the right, the RAG backend provides a detailed response, including memory types, capacities, and interface speeds. Let's ask how many media decoders an Intel Gaudi 3 has. The non-RAG backend gives an incorrect answer, while the RAG backend provides detailed information on the number of decoders, supported video formats, max resolutions, and post-processing capabilities. This extra context showcases the power of RAG for inferencing. Here is an overview of the information flow. A PDF is scanned, text is extracted, chunked, and embedded into a vector database. When a user queries, relevant data is extracted, a new prompt is built, and the LLM model provides a more accurate response. Intel Gaudi 3 is a cost-effective solution for inferencing both small and large AI models. This video is a proof of concept showing an Intel Gaudi 3 working in a Red Hat OpenShift environment. Thanks for watching.